We are in Rosen, section 5.3 on recursion relations and structural induction. We are going to prove an important theorem related to the uh, complexity of the Euclidean algorithm. This is Lemay's theorem, and it states that if you have a and b positive integers with a greater than or equal to b, then the number of divisions used by the Euclidean algorithm to find the greatest common divisor of the two numbers is less than or equal to 5 times the number of decimal digits of b, the smaller number. Okay, well, let's remember how the Euclidean algorithm works. We will um, apply that on the left-hand side with a greater than or equal to b, and we start with a being R0 and b being R1, and it's going to take n divisions to get down to the stopping condition before we find our greatest common divisor, which is Rn. All right, so it turns out we're going to be able to relate these remainders to the Fibonacci numbers and eventually b to a specific Fibonacci number. So let's start with considering the bottom. We have each quotient q is less than or equal, is at least 1, is greater than or equal to 1, and the final quotient q sub n is greater than or equal to 2. Because if it was 1, then we would have stopped one step sooner. All right, so let's first talk about r sub n. Since r sub n is our greatest common divisor, it's greater than or equal to 1, and 1 is Fibonacci 2, so Rn is greater than or equal to Fibonacci 2. Rn minus 1, we can see it over here, it's equal to Rn times Qn, and since Qn is at least 2, Rn minus 1 is greater than or equal to twice Rn, and that is greater than or equal to twice Fibonacci 2, but twice Fibonacci 2 is Fibonacci 3. I want you to notice the indices that we're setting up here. The index of the remainder and the Fibonacci number it's greater than all add to n plus 2. N minus 1 and plus 3 is n plus 2. Okay, so if we do the next one, our n minus 2, it's equal to, you can look at it over here, Rn minus 2 is equal to Rn minus 1 times Qn minus 1 plus Rn, and that means it's going to be, Rn minus 2 is going to be greater than or equal to Rn minus 1 plus Rn, because Q could be greater than 1. Well, Rn minus 1 is greater than or equal to F3, Fibonacci 3, and Rn is greater than or equal to F2, and the sum of those is Fibonacci 4. So Rn minus 2 is greater than or equal to Fibonacci 4, and you see their indices sum to n plus 2. Well, that index relationship will just continue all the way down. So R2 is greater than or equal to R3 plus R4. R3 is greater than or equal to Fn minus 1. R4 is greater than or equal to Fn minus 2. And their sum is Fn. So R2 is greater than or equal to Fibonacci n. You can see that their indices add to n plus 2. And b, which is R1, is going to be greater than or equal to R2 plus R3, which is greater than or equal to Fibonacci n plus Fibonacci n minus 1 to give us Fibonacci n plus 1. So R1, which is b, is greater than or equal to Fibonacci n plus 1. In other words, if it takes n divisions for the Euclidean algorithm, then b must be greater than or equal to Fibonacci n plus 1. So Fibonacci n plus 1 is the lower bound on b if n divisions are needed to find the greatest common divisor. And then remember, uh, earlier in the chapter, we noted that Fibonacci n plus 1 is always greater than alpha to the n minus 1 for large enough n, where alpha is this value right here. So since b is greater than or equal to Fibonacci n plus 1, that means it is strictly greater than alpha to the n minus 1. And so if we consider that value, if the log of that value alpha is approximately 0.208, that's greater than 0.5. Now we're going to take the log base 10 of both sides of this, and we bring the exponent out front. Log 10b is greater than n minus 1 log 10 of alpha, but that is greater than n minus 1 divided by 5. So if I multiply both sides by 5, I get n minus 1 is less than or equal to log 10b. So in some sense, b forms an upper bound on n, the number of divisions for the Euclidean algorithm. Now if b is k decimal digits, then b is less than or equal to 10 to the k. That means log 10b is less than, it's not less than or equal to, is less than 10 to the k. That means log 10b is less than k. So I will substitute that and say that n minus 1 is less than 5k, which is the number of decimal digits of b. And since n is an integer, we can drop the n minus 1 and make it a non-strict inequality. N is less than or equal to 5k, and the result is proven. And so we can say that the Euclidean algorithm has big O of log of b divisions, and where b is the smaller of the two numbers. And this is considered the first result in computational complexity. That's pretty neat. And there's a proof of Lemay's theorem.